The oceans represent nearly 70% of our planet. However, we are far from knowing them. We know much more about some planets in our solar system than we do about the great expanses of water on Earth. It must be said that the technical means we have at present do not allow us to easily explore the ocean floor. However, we have learned a lot about the fauna, the flora, and the geological constitution of the seafloor in recent years. In order to better find our way in this blue immensity, men have divided the oceans into 5 large parts: Pacific, Atlantic, Arctic, Southern, Indian. The depth of the oceans varies according to the territories and the submarine reliefs constituted by oceanic ridges, volcanoes, but also plains. If the ocean depth does not go deeper than 200 meters, or 650 feet in some places, the abysses can reach up to 11,000 meters, or 36,000 feet deep, in the Mariana Trench, located in the Pacific. 1.386 billion square kilometers. That is more than 320 million square miles. This is the amount of water in the oceans. 2% comes from glaciers and eternal snows. And all this, that's without counting the lakes, ponds, marshes, rivers, soil moisture, or water in the atmosphere. Water is one of the most important elements on our planet. But our planet has not always looked like it does today. Far from it. If we walk on a planetary scale and see the world ocean as a big whole, a single unit, then you should know that 50 to 80% of our world's species are found there. It also generates a large part of the ecosystem services of our planet. That is to say, that more than half of the ecological functions, air oxygenation, carbon sequestration, nutrient recycling, biomass constitution, necessary to life on Earth, come from the oceans. This is undoubtedly a good reason to preserve it and to take great care of this invaluable resource. But it is also a very good reason to try to know more about it, and especially about its history. That's what I invite you to discover in this video. Our history and his are closely linked. Dear traveler, welcome. Today we are going on a long expedition into the past to explore the seabed before our era. What might the aquatic animals that roam the Earth's waters millions of years before us have looked like? Do you have any idea what the world's oceans looked like in prehistoric times? In your opinion, is it so different from what we know or imagine today? To find out, make yourself comfortable. Remember to like the video and subscribe to the channel so you don't miss anything. Our epic adventure starts now. $3 billion tons of water. This is probably what earned the Earth the nickname of Blue Planet. However, it has not always had such an abundance of water. A few billion years ago, it was still only rock. If we are not yet completely sure and certain of the anniversary of the birth of the ocean, we know, since 1999, thanks to the discovery of a zircon, that water was already present in quantity 4.5 billion years ago. Indeed, the crystallization of this mineral necessarily requires the element water in the liquid state. However, this zircon would celebrate its 4.4 billion candles. In addition to its impressive age, this zircon becomes the indisputable proof that water was indeed present during this period. On the other hand, going back a little further and finding irrefutable proof of when the first ocean, the primitive ocean, was formed is still difficult to find. What caused the ocean to form is also still a matter of debate among the big names in science. There are, so to speak, two teams, two camps, two hypotheses which are both perfectly plausible. This is why the debate is still open today, even if certain elements of study and research will undoubtedly shed light on this mystery in the near future. The first hypothesis evokes a brutal volcanic degassing and puts forward the fact that the Earth already contained a certain quantity of water buried in its entrails. The Earth's water was integrated into the magma of our deep Earth's layers. Meteorites, when they collided with the Earth, also brought this essential element for life: water. The Earth in the first millennia is very different from what we know today. Neither water nor even oxygen are present. It is only rock. A huge rock in the middle of the universe without life. It is constantly bombarded from all sides. Paradoxically, it is these collisions and these multiple impacts that have triggered certain events. At the beginning, the planetoids which rush on the Earth and bombard it unceasingly will cause a heating and the fusion of the rock. After several thousands of years and several combinations of events, the Earth will begin to cool on the surface. It is still very hot and under high pressure, but it is no longer incandescent. If the Earth is a real molten rock, it is also riddled with volcanoes. As you've seen, our planet's original crust has been repeatedly bombarded by meteorites, and that eventually led to consequences: awakening volcanoes and churning geysers. Imagine all that pressure and heat being released all at once all over the Earth. The steam that is released is then colossal and forms gargantuan clouds. When the Earth finally started to cool down, all the parameters were there to let these clouds shed their water. A deluge of water, day and night, night and day, for several million years. Torrential rains fall on the Earth. Oceans, lakes, rivers finally appear. The planet reveals a new face. But for some scientists and geochemists, this theory does not hold water, at least not on all points, and they want to prove it. The Moon. Yes, you may not know it, but according to scientists, our satellite is actually a small fragment of our planet. The impact of a protoplanet, known as Theia, against the proto-Earth would have created a ring of debris that eventually gathered into a single natural satellite, the Moon. Now, if this hypothesis is true, it also means that if water had been naturally present on Earth, it would have had to be vaporized and incorporated into the debris cloud that formed the Moon. Despite the years, we would find a presence of this water on the Moon. But this is not the case. It is only a dry rock without any drop of water, neither on the surface nor in the rock, in any form whatsoever. If this hypothesis is verified by astronomical and physical research, it would mean that water would not have sprung up only from the depths, but would have been brought mostly by the sky, thanks to meteorites, comets, and asteroids, during an event known as the Great Lake Bombardment. Most of them contained ice, at least 10%, which would explain the arrival of water on Earth. The common denominator of these two hypotheses remains the role of volcanic eruptions and geysers on the formation of clouds. The collisions and the pressure inside the rock are such that the planet will leave cracks in order to evacuate the internal heat that it has stored. Volcanic eruptions and geysers then begin their ballet. In turn, they launch themselves into this massive bubbling effervescence. Clouds of gas and water vapor come out of the Earth everywhere. The planet seems ready to implode. The water, thanks to the runoff, is washing away the rock and loading itself with salt. The oceans took about 150 million years to form. They were then heavily loaded with iron, and the color green predominated. Water is abundant and allows the cooling of the planet, and especially of the lava. The granitic rocks float on the Earth's mantle, which will lead to plate tectonics and continental drift. When we say that water is necessary for life, we don't mean it so well. It is at the origin of many other phenomena, including plate tectonics. About 360 million years ago, the distribution of land and sea was quite different from what we know today. All this took place long before the creation of Pangaea. At this time of the Cambrian, during the first phase of the Paleozoic, the Lapitous Ocean separates North America from South America and Africa, which was welded together, the whole called Gondwana. The Rheic Ocean separates the African coast from the Baltic continent. Other oceans, such as the Panthalassa and the Paleotethys, cover a very large area that separates North China and Siberia. Over millions of years, the continents have moved apart, the oceans have expanded, and opened on others. The land broke away, and microcontinents were born. This is the case in the Devonian of Avalonia, which includes Canada, England, Wales, France, and Denmark. In the Carboniferous, North China shrank and became isolated from the other continents and microcontinents. During the Permian, new movements started to bring the lands closer together to form Pangaea. In the Triassic, the Tethys Ocean is cut. It begins an opening that will lead to the Atlantic Ocean by dislocating the Pangaea. Plate subductions, when one plate slides under another, and orogenies, these movements of plates that lead to the formation of mountains, continue to shape the planet and give it a new face over time. Ocean ridge activity keeps sea levels high. Shallow seas cover some continents. Other phenomena cause basalt flows. Continents break off one by one. The land and water seem to be in perpetual motion. Each of these movements will lead the continents a little more adrift to form the world as we know it today. The Paleozoic eon, and especially the first period of the Paleozoic, the Cambrian, marks a real turning point for life on Earth. Until then, unicellular organisms were the only ones to populate our planet. None of them has a particular cell that would allow, for example, to produce internal organs. They are soft-bodied, protozoic beings. They feed via the cell membrane, which is their own body. The Cambrian marks an extraordinary and unprecedented change, the birth of multicellular organisms. In addition to the appearance of these new living beings, the Cambrian is also synonymous with the explosion of life, which proliferated during this period. In summary, what you should remember about the Cambrian era is that life is teeming and diversifying all over the world. Animals are still largely soft-bodied organisms, but their differentiated cells allow them to adapt to their environment and evolve. specific internal and external organs appear. Eyes, legs, antennae, mouth system, digestive system, nervous system. A food chain is also set up, and thus favors the development of life in the ocean. The Cambrian is a pivotal period, a key element in our history. The Cambrian era, you will have understood, makes our planet take a new turn. The Cambrian marks the beginning of the primary era, but also, and especially, an explosion of underwater life. Organisms develop, they multiply, they evolve and adapt to their environment and to a new way of life. Some of them will be equipped with a skeleton, others with shells or carapaces. For these animals, it is a new way of approaching the environment and of fighting for their survival. But for us humans, it also means that we will be able to find traces of their life on Earth much later. This was not the case before. That is why it is still so difficult to determine the extent of underwater life in the Precambrian. But 540 million years ago, a new form of life developed underwater. They can finally leave shell impressions or traces of their skeletons, elements that will fossilize over time and become the first witnesses of underwater history. To discover this history and to meet your first living Cambrian organisms, I will take you to Canada. There, a 525-million-year-old rock has offered its most beautiful prehistoric treasures. When we talk about prehistoric animals, we more easily evoke the Jurassic, the cinema helping, or the Cretaceous. However, many other animals, just as fantastic and important, have marked the history of the Earth. Let's go now to Canada. We are in the Rocky Mountains of Yoho National Park, on the western slope of Mount Stephen in Canada. It was here in 1909 that Charles Doolittle Walcott, a British paleontologist, made an absolutely incredible discovery. There was such a large pool of fossilized marine animals that it was given a name: the Burgess Sea Trough. The quantity is important. Nearly 65,000 fossil specimens in all, belonging to 120 different species. But the quality is also just as spectacular. The majority of the fossils are a bit damaged. It is rare to have a whole skeleton perfectly preserved. Time has done its work, and geological and climatic changes have inevitably had an impact on the remains of the past. Yet in the Burgess fauna, time seems to have stood still. The footprints are remarkable because the soft parts of the animal in question can also be seen, which is very rare. The phenomenon is explained by a slow decomposition of the animals. The shales in which the fossils were found were not formed gradually, but through a series of brutal and intense mudslides. The soft parts were isolated from the oxygen in the water, which slowed down the decomposition of the bodies. Fast burial and slow decomposition is the winning combo for preserving fossils over millions of years. Now that you've learned about these early fossils, let's take a trip down memory lane. Are you ready to go to the Cambrian? On the geologic timescale, we are now between 359 to 299 million years old. As you can see, things look quite different. The average global temperature is 25 degrees Celsius or 77 degrees Fahrenheit. If this kind of climate seems mild, there is no life on the ground. Look at the continents. All is rock, emptiness, and solitude, as far as the eye can see. This is easily explained. At this time in our history, the ozone layer is so thin that it does not protect the planet from the sun's ultraviolet rays. The slightest hope of life that could have shown up on the surface would have died, victim of our solar star. The waters are relatively warm, and the atmosphere contains a little oxygen and very little CO2. In spite of rather difficult conditions, they have nevertheless allowed life to proliferate. This is still impossible on the continent, but the ocean is full of all kinds of marine specimens. The first fossiliferous animals, i.e. capable of leaving fossil traces, arrived in the ocean. Who would have thought that the invention of the shell and the carapace would be so significant? Invertebrates are king and populate most of the warm and shallow seas. The first green algae develop, as you can see. They are unicellular or multicellular algae. They were limited to the shores and lines of the coasts where they formed a short carpet, like our modern bryophytes. These algae serve as a food base for a large number of species. Nature set up the first food chains with primary consumers, vegetarians, and secondary consumers, carnivores and predators. Let's go deep into the warm waters of the Cambrian to discover these seabeds. You can see worms, sponges, mollusks, and echinoderms. These major groups of animal classification are still present today, but there are groups that did not survive and ended up disappearing. These are the ones we will see first. Let's start with the trilobite. The trilobites owe their name to the shape of their body. They are made up of a median lobe and 2 lateral lobes. They live near the seabed. They are not easy to see in these funds. Here is a small specimen, 5 centimeters or 2 inches approximately. It is a Cotycops fernandini. Some members of the trilobite group are much smaller, only 1 millimeter. Other large specimens can reach 70 centimeters or 28 inches. This Cotycops fernandini seems quite fragile in this complex and primitive environment. It is, however, perfectly adapted to its environment. Its eyes are equipped with many facets which enable it to see 360 degrees. Impressive, no? This faculty undoubtedly allowed him to facilitate his research, to feed himself more easily. It could probably have survived despite the mass extinction that occurred at the end of the Permian, the last phase of the Paleozoic, in the salty waters of the ocean. Unfortunately for it, it did not venture into fresh water, and therefore did not survive. Here is another member of the arthropod group. It is the Yohoia tenuis. It is very small, between 7 and 23 millimeters only, so it is difficult to see. But if you get a little closer, you should be able to meet some. They were quite numerous in this part of the ocean. They occupied the sandy and muddy bottoms. This small animal has some assets to compensate for its small size, notably a cranial shield and 13 tergites. The tergites are sclerites, i.e., polycrystalline plates. They harden thanks to a process called sclerification. The tergites are sclerites which are located at a particular place of the body of the animal. We find them on the back, and they enclose its abdomen. Our specimen of Yohoia tenuis has 13 tergites. The first 10, as you can see, end in the form of a point on the sides. The last 3 form a tube, which protects this part of the body. Its tail is shaped like a paddle. To feed itself, it uses the small appendices that you see at the level of the skull. They look like small bent legs and some kind of fingers at the ends. They could thus manage to capture prey, feeding only on dead animals. Here is now the last of the group, the Canidaspis. It is not the least important because it seems to be one of the oldest crustaceans. As you can see, it moves by walking on the seafloor. It is a benthic feeder. It uses its appendages to stir up the mud and find food. Let's look at another group, the Archaeocyatha. The Archaeocyatha are the first reef-building metazoans. A reef is a chain of living organisms, like the coral reefs we know. The Archaeocyatha are not corals, however. They should not be confused. They are calcareous sponges. The sponge is made up of a calyx, a kind of porous cone, nested one inside the other to form an internal and external wall, and thus protect the organism living inside. Some specimens occupy the whole calyx. Other organisms occupy only the upper part of the calyx. There are many species in this group. These sponges feed by filtration. Zooplankton, phytoplankton, and organic particles in suspension constitute their diet. Fragile, they can only survive under very strict conditions. They cannot tolerate any change in temperature, salinity, salt content, and depth. This is undoubtedly what led the species to its loss. It is probably the first super predator of our planet. The Anomalocaris is not very aesthetic and lacks a bit of charm, but to feed, it is better to be powerful, skilled, fast or fine strategist than cute. This strange shrimp is about 1 meter or 3 feet long. Anomalocaris has 2 large black eyes that allow it to interact with its environment. Its sight is not very clear, and it probably doesn't perceive the landscape very well from far away, but its eyes allow it to flush out its victims. Its mouth is a real cutthroat. It is equipped with sharp bone plates to crush its prey. Let's go back to the surface and let this Anomalocaris go about its business. It perfectly symbolizes the enormous evolutionary leap of living organisms since the Cambrian. We are going to leave the Cambrian era to meet the aquatic animals of the next era, the Ordovician. The Ordovician is the second of the 6 geological systems that make up the Paleozoic. Differentiating the geological layers allows for a better understanding and appreciation of the environment in which we find ourselves. Until the 1800s, the Cambrian preceded the Silurian. Then in 1879, Charles Lapworth understood that another phase lay between the two. The global ocean and land cooled. Vast reservoirs of oil and gas appeared. There was also a new explosion of underwater biodiversity. This is why it was essential to differentiate it from the other two. On the geological timescale, the Ordovician is located between -485 to -443 million years. The Baltica and the Laurentia will collide. Towards the end of this period, Gondwana was close to the pole and largely covered by glaciers. At this point in the history of our oceans, sea levels were higher than in the Cambrian, and temperatures had risen to 30 degrees Celsius or 86 degrees Fahrenheit at the surface of the globe. The number of genera and families of living beings tripled or even quadrupled compared to the previous era. What also marks the arrival of the Ordovician is the appearance of Lapitognathus fluctivigus. It belongs to the now extinct family of conodonts. This species finally resembles a species that we know today, the eel. What allows to differentiate it, they are its head and its teeth. For a long time, the only fossils found were its teeth. From then on, it was difficult to imagine the rest of its body from a simple jaw. Since then, we have some elements that have allowed us to define the soft part, and thus to estimate that it is similar to a kind of eel. Although the species has teeth, scientists think that it was mainly used as a filter to feed on plankton. After studying the body, it is unlikely that the animal is classified as a predator. Other groups, which had already appeared in the Cambrian but were still very few in number, developed during the Ordovician. This is the case of the articulated brachiopods, cephalopods, crinoids, ostracods, bryozoa, graptolites, conodonts, as we have seen previously, and of course, corals. The first ectoprocts appear at the same time. They are what we call moss animals. They are sessile and live in a fixed way on a rocky element, for example. The body of an ectoproct gathers a very large number of small animals called zooids. This is called a colony. Each zooid lives in a small lodge made of limestone. It is these lodges connected to each other that form the skeleton of the colony. The colonies can take different forms, similar to corals, to moss, or even to lace. The corals were isolated until now. They will start to develop more widely. Here you can see the first coral reefs in the ocean. As you can imagine, these reefs are home to life. You can find the first bivalves near these primitive corals. If the bivalve family already existed in the Cambrian, it evolved and developed largely in the Ordovician. The shell of a bivalve is composed of calcium carbonate and includes two parts, generally similar, shell equivalents, which are called valves. These are joined along one of their edges by a flexible ligament. A strong increase in the diversity of bivalve species is accompanied by the appearance of disodonts, heterodonts, and taxodonts. Among bivalves, we can recognize the Raffinesquina in a half circle, or the more elongated Modiolopsis. Other mollusks, such as gastropods, are developing. This class of mollusks is characterized by the torsion of their visceral mass. They have a very wide variety of forms, but can be recognized generally by their characteristic twisted, univalve dorsal shell when present. They have a foot and a distinct head. Their foot is flattened in a broad ventral sole, which makes them excellent swimmers. Their head, it comprises eyes and a radula. Here is Stepsodiscus, and a little further, Chippewela, both aquatic snails. I would now like to introduce you to another animal with a shell, but this one is much larger and known for its hunting prowess. The Orthoceras reached disproportionate sizes. Here is one of the largest Orthoceras of its category, the giant Orthoceras. It bears its name well. If the living quarters of the cephalopod could reach 2 meters or 6 feet long, the shell was around 10 meters or more than 30 feet. This Orthoceras is rather impressive. It was a formidable predator and quickly rose to the top of the food chain. It could be compared to an octopus or a gigantic squid. To hunt, it used its tentacles to capture its prey. Then it devoured it with its beak. Living in deep water, this animal had a very bad sight. But as for the majority of the living beings in this case, other senses compensate this handicap. With him, it is the sense of smell. He smells from far away his future victims, which become his dish of the day. We did not see much vertebrates until now. even if mollusks are very present, vertebrates are becoming more and more important in the ocean. Here is one of them, a fish of the genus Agnathis. This means that it has no jaws, but it has no trouble feeding for all that. The mouth of Sacabambaspis genvieri was lined with nearly 60 rows of small bony mouth plates that were probably movable to provide an effective sucking action through the expansion and contraction of the oral cavity and pharynx. It looks somewhat like a tadpole with its large head, flat body, and wagging tail. A big tadpole of 25 centimeters long, that is to say, almost 10 inches. We have just started this journey, and yet events are already getting complicated on land and at sea. At the end of this period, the planet experiences the first mass extinction and the second largest ever known. Between 60 and 80% of marine species will disappear. The cause? A drastic decrease in atmospheric CO2, leading to a global cooling. Indeed, one of the factors preventing ice ages in this era is the high concentration of CO2 in the atmosphere, which at the time was 8 to 20 times higher than pre-industrial levels. It is difficult to establish the exact cause, but one plausible hypothesis is that non-vascular plants settled and developed on land during the late Ordovician. This major modification of the biosphere would have accelerated the process of silicate alteration on the continents. This process, by fixing very large quantities of carbon dioxide, would have led to a decrease in the Earth's temperature and the development of polar caps. The consequences continue, since the ice sheets increase the albedo of the Earth, reflecting more of the sun's rays, thus aggravating the drop in temperature. Another theory is that a large continental volcanic activity has caused basaltic flows in the Katyan igneous province. This tilting is at the transition between a period where the continental masses were very dispersed and where a warm climate prevailed, and a cold period that begins during the Katyan and will culminate with a Hernantian glaciation caused by the migration of the supercontinent of Proto-Gondwana to the South Pole. These volcanic activities would have released large quantities of CO2 into the atmosphere and would have replaced granitic rocks by basaltic plains. The problem? Basaltic rocks erode much faster than granitic rocks, which means that they store much more atmospheric CO2. Soon the level of atmospheric CO2 decreased, falling below the levels of pre-volcanic activity. However, this glaciation caused the sea level to drop by several hundred meters. Average global surface temperatures dropped from 30 degrees Celsius to 10 degrees Celsius, or from 86 degrees Fahrenheit to 50 degrees Fahrenheit. Creatures that had made their homes in the deep ocean would have witnessed the cooling and shrinking of their habitat, and would have found themselves without a way out. The rate of extinction of marine animal families in the Upper Ordovician over about 20 million years is the highest ever recorded in the history of the Earth, on the order of 20 families per million years. The glaciation lasted between 1 and 35 million years. The survivors would have had a hard time recovering in these chemically hostile waters. Once the sea level started to rise again, the levels of dissolved oxygen in the water decreased, which would have increased the absorption of toxic metals in the oceans. This anoxia would have killed many of the survivors of the first wave of extinction. Following this extinction occurs a new geological phase, the Silurian. Over millions of years, CO2 is gradually re-injected into the Earth's atmosphere, warming the planet and ending the Ice Age. After this mass extinction, life proliferates again in the ocean. It proliferates and diversifies. Coral reefs can be admired, especially near the coasts of the Panthalassa Ocean and those of Paleotethys on shallow seabeds. The climate is mild, 20 degrees Celsius or 68 degrees Fahrenheit on the thermometer. The corals, especially the roughy and the tabulate, are very happy in the sea. The first one has a calcareous skeleton, a rocky element. It was solitary and becomes more and more colonial, hence the constitution of reefs. For the second, its exoskeleton, an external skeleton, is made of calcite. Did you notice the fish that just broke away from us by moving behind the corals? It is the Pharyngolepis oblongus. It belongs to the family of anapsids. It measures about 25 centimeters. If it has an anal and caudal fins, it does not have pectoral fins, but bony spines. It is undoubtedly a means of protecting itself from the predators for this fish, which feeds on the ground in the marine funds. A little further on, you will be able to see another kind of fish that also populated this part of the oceans. These jawless fish are part of the species that lived in saltwater, but also in the freshwater of rivers. Do you notice the cranial shield of this Adeolaspis tessellata? Despite its needle-like shape on a good part of its body, it is indeed a fish. It has two fins that allow it to move in the water. We also find other fish of the same type, like the Cephalaspis, which appreciates the estuaries. It is part of the detritivores. Far from being at the top of the food chain, it protects itself from predators thanks to its cranial shield. But this was not its only use. Indeed, his shield had sensory plates along the edge and center, which were used to detect the presence of worms and other burrowing organisms in the mud. But during this period, it wasn't just jawless fish, quite the opposite. One of the highlights of the Silurian is the appearance of jaws in vertebrate fish. The first to be constituted of this famous jaw, which starts from the second branchial arc, are the acanthodians with spiny fins and the placoderms whose front of the body is enclosed in a bony carapace. Some of these fish had a bony skeleton, others rather cartilaginous. They are numerous and very diversified in this branch. You can see here Cheracanthus murchisoni. But we will fix our attention on this Climatius. It is a spiny shark. Rather good swimmer, it was also a fine hunter. It feeds mainly on other fishes, but does not make the fine mouth in front of a crustacean. What is rather surprising about him is precisely his jaws. The lower jaw is equipped with multiple sharp teeth. At the slightest sign of wear, the teeth fall out to make room for a new, perfectly sharpened tooth. The upper jaw has no teeth at all. Another category of creatures marks the Silurian. They are the Eurypterids. They already existed in the Ordovician, but the Silurian is their finest hour. It is at this period that they are the most numerous, and especially the most varied. Here is one of them, an Acutoramus. This beautiful specimen measures already 2.5 meters, that is 8 feet. It is the largest arthropod known so far. In addition to having rather extraordinary dimensions, it had a fast and efficient swimming technique. Its last pair of legs constituted real paddles, while its abdomen undulated, to make it gain in speed and mobility. As for feeding, it also had some assets to get by in the sea. Its chelicerae, small appendages located on the skull in the shape of a hook or a claw depending on the species, are nestled under its head when it is at rest. But in case of hunger, it projects them on its prey. These two cephalopods should undoubtedly be wary. Phragmocharis eurystoma and Phragmocharis dubium have a pretty shell, curved in the shape of a Phrygian cap. But it will be of no use facing the monster which prowls in these waters. The armored fish have made their grand entrance. These fish have a thick bony armor on their head and thorax. The plates of this armor allowed them to protect their vital organs such as eyes, brain, heart, etc. from attack by predators, and perhaps sometimes even fellow fish. These fish were not very difficult. They frequented reefs, deltas, as well as the open sea. Their diets were just as varied. Some grazed on algae, others crushed mollusks, others were carnivorous. Entelognathus primordialis is one of the first placoderms. Its head and its body were covered with thick plates, while its tail carried scales. It had jaws but no teeth, and its small eyes were buried in large deep sockets. Each new geological phase has its milestone and a new facet of the Earth. This time it is the appearance of mountains in two different places. The first orogeny, phenomenon of mountain formation, takes place in the Lapitous Ocean after the collusion of two continents, Laurentia and Avalonia. The second also includes Laurentia and Amorica. Two oceans close, the Lapitous and the Rake. Elsewhere, they are slides of oceanic plates under neighboring plates that occur. Several physical reactions follow one after the other, making the world evolve. The temperature is increased considerably and is approaching 30 degrees Celsius or 86 degrees Fahrenheit on Earth. It must be said that with our heads underwater, we have not seen how much things have changed on the surface of the continents as well. Vegetation has grown a lot, and photosynthesis is working, so carbon dioxide levels are falling. The vegetation is small for the moment, but during the Devonian period, we find the beginnings of the forest. Stromatopores, tabulate corals, and tetracolariar corals continue to build the reefs. They are growing, diversifying, organizing themselves, and can thus welcome and shelter new species. Brachiopods and other shell specimens are still evolving in Devonian waters. The armorfish proliferate. We can see here a Bothriolepis, and a little further, a Dunkleosteus. Let us approach first the Bothriolepis. This one seems to be a Bothriolepis canadensis, to be precise. It is a small benthic animal. In other words, it roams the seabed. It prefers fresh water and is part of the detritivores. This small marine animal feeds on animal, plant, and fungal debris. In short, any organic element in decomposition. It measures about 30 centimeters or 10 feet in general, but can reach 100 centimeters or 40 inches for the largest species, Bothriolepis maxima. Let's take a closer look at Dunkleosteus, which is part of the placoderm family. Dunkleosteus was an armored fish. The armored fish, if they appeared in Silurian, reigned supreme in Devonian. They became the kings of the oceans and challenged the great Eurypteroids, which until then were the most dangerous predators. One of the most formidable of these armored fish is the Dunkleosteus. This cartilaginous fish is one of the first of the genus Condycthes. It has paired fins, paired nostrils, scales, and a serial chambered heart. You see the fins? They go in pairs on each side of its body. It has quite large eyes and small but sharp teeth. It feeds on fish and can live in a group. This one must be Cladocelicae elegans. Despite its size between 60 and 180 centimeters, that is to say between 20 and 70 inches, it is the favorite prey of the mastodon of the seas, the Dunkleosteus. The fish with radiated fins continue to populate the oceans, like this Actinopterygenian, Carolepis. Others, like the fish with fleshy fins, have undergone an extraordinary evolution. It is the lungfish. They are pulmonate fish. In addition to gill breathing, these fish have a lung. This kind of fish knows very different morphologies. Here is a Lepidosaurin, Paradoxa. Rather long, it has a median fin which surrounds the posterior part of the body. It also has pectoral and pelvic fins, but they look more like thread-like excrescences. Here is another congener of the same family, the Neoceratodus forsteri. It is much more stocky, but it is indeed part of the same family. Another particularity of this fish is its ability to breathe in the open air with as much ease as going down to 30 meters or 100 feet underwater. It is able, for example, to crawl in the mud, or for certain species of lungfish, to create a burrow in the mud, to manufacture a cocoon by secreting a mucus which seems assimilated to a living tissue with antimicrobial properties. All these extraordinary faculties have undoubtedly helped it to survive, in spite of the climatic and physical changes that the planet has undergone over the millions of years that followed. On the geological timescale, we are now between -359 and -299 million years. It is during the Carboniferous period that Pangaea appears. Almost all the continents are welded into a single continental mass. Another element to remember about this geological phase is the important transgression of the warm waters of the Paleothus on the continental platforms. It allows many coral reefs to develop. Erosion also brings many changes. It favors the formation of mountains, but also vegetation. The amount of CO2 will therefore largely decrease, and at the same time, lower the temperature of the planet, which is now about 15 degrees Celsius or 59 degrees Fahrenheit. If the family of arthropods, like the trilobite that we were able to discover in the Cambrian, is losing speed and is coming to an end, other marine specimens continue to evolve. Because of the constitution of coral reefs, the population of certain groups of marine animals proliferates. Brachiopods, echinoderms, and mollusks, for example, reside in these warm waters. Here is a member of the brachiopod family, the Productus subaculeatus. Its shell is very small, between 12 and 24 millimeters only. It walks not far from what looks like a plant from afar, but which is not quite one. Crinoids have a morphology that reminds a plant. It is to this resemblance that they owe their name. Crinoid means sea lily. The stem can be more or less long and the roots are fixed in the seabed. At the other end, we can see a crown. It is made up of the various branched arms of the crinoid. It is a real shelter for many marine animals, like gastropods, for example. If its arms form a refuge, they also allow it to feed on plankton by filtration. The stem constitutes a calcareous skeleton. This specimen, as you may have guessed, is part of the shark family. The most impressive thing about this fish is without a doubt its jaw. Look closely. You will notice that its lower jaw is shaped like a circular saw. This does not bode well for other small vertebrates that cross its path. Another rather oddly shaped shark family is the Stethocanthus family. Here is one of them, a Stethocanthus altonensis. Its dorsal fin looks like a kind of anvil. Was it to frighten its potential predators, or a charming asset for the reproduction period? Difficult to say. This specimen is one of the first cartilaginous fish that swam in the ocean. It shares this small feat with a Cladocelecki and the Gladbacchus. It appreciates very much small fishes, but also primitive amphibians that it managed to hunt without too much difficulty. We now come to the last geological phase of the Paleozoic, the Permian. This period is between minus 299 and minus 251 million years old. Pangaea is finished. The temperature oscillates between 15 and 18 degrees Celsius, or 60 degrees Fahrenheit. Oxygen in the atmosphere continued to increase, no doubt thanks to the vegetation of the continent, which continued to conquer the smallest square kilometer on the surface. The reefs are a real marine breeding ground. They are essential for the survival of many species. Corals, of course, help their development, but they are far from being the only ones. In this intertropical zone, you can see a big yellow sponge. No, it is not a rock, but a gigantic sponge. This one is probably around 2 meters or 6 feet. Many filter feeders reside here. We can see brachiopods, but also mollusks. The one you see here is Cuperoceras texanum. As you can see, this species has developed spines all along its shell. This provides an effective defense against certain predators. These fish with cartilaginous skeletons have been around for several million years now, and they continue to develop in the Permian. They have muscles adapted for swimming, increasingly developed sensory organs, and a powerful jaw. Hybotus is very similar to the shark we know today. It could reach 2 meters or 6 feet in length. An outstanding predator, its morphology allowed it to hunt many types of prey. The shape of its teeth allows us to believe that it fed as well on fish as on other marine animals. Here is another specimen of the same family. Despite its appearance, Orthocanthus is indeed a primitive shark. It has a rather long and slender body, but it also has sharp teeth. Unlike the previous fishes, these are fishes with a bony skeleton. Another specificity of this family of vertebrate fishes, the rhyid fin, i.e. with a rigid bony part. Here is Adula blainvelli. It measures between 5 and 20 centimeters, or between 2 and 8 inches, for the adult specimens. Its dorsal fin is in the continuity of the anal fin. It also has ventral fins, but they are rather small and thin. It was undoubtedly a good swimmer. This faculty was surely an essential survival technique in order to flee its numerous predators, like Actinodon, a temnospondyli amphibian, or sharks, like Exploracanthus. We have not mentioned this family until now. It appeared in the Carboniferous, but it developed mainly in the Permian and Triassic. Some of them are only a few centimeters or feet long, while others are close to 10 meters or more than 30 feet. As you can see, this category is very varied. As incredible as it may seem, in this class, there is a family of temnospondyls. They are carnivorous and have made a place for themselves on land, as well as in the sea and freshwater. Here is one of them, an Eriops megacephalus. It is quite impressive, isn't it? It can measure up to 3 meters or 10 feet and probably weighs more than 200 kilos or 440 pounds. Its huge mouth doesn't let you know what's inside. But if you get a little closer and open its jaw, you will see that it has many curved teeth. Incredible for an amphibian, right? They also have an enamel with a pleated pattern. Even its palate is formidably equipped. There are 3 pairs of fangs curved backwards. It's a real trap for even the slippery prey. None of the aquatic animals that we met seem to realize the drastic changes that are taking place and the serious consequences that they are about to undergo. The reunion of all the continents in a single block causes a generalized reduction of the sea level. The formation of Pangaea thus leads to the reduction of the surface of the seas, which were largely populated. The sea level drops by 250 meters, or more than 820 feet. The seas are then shallow, the waters stagnant and warm, poorly oxygenated, and therefore unfavorable to animal life. The warm currents around the South Pole and the increase in the CO2 content of the atmosphere have allowed the polar cap that used to cover the pole to melt. These changes lead to others. The ice caps are no longer there, or too few of them to reflect solar energy back to space. Intense volcanic eruptions follow one another and enrich the atmosphere with CO2. Global warming is underway. The greenhouse gas has combined with CO2 to increase the intensity of this warming even more. The increase in ocean temperatures has destabilized the methane deposits stored in the ocean floor. Huge eruptions of basalt are taking place in Siberia, spitting more and more CO2 into the atmosphere. The greatest biological crisis of all time is underway. Nothing can stop it anymore. Much less known than the disappearance of non-avian dinosaurs, the Permian-Triassic crisis is nevertheless the most deadly. The Permian-Triassic extinction is one of the most deadly, perhaps even the most severe, that the world has ever suffered. 90% of marine species, 75% of vertebrates, almost all primitive amphibians will be wiped off the face of the earth. After this crisis, nature takes its rights. Life takes its course. Nothing is simple. It takes time. But nature is amazing. We are now entering the Mesozoic. It is located between minus 251 and minus 66 million years. If the beginning of the Paleozoic marks a turning point for living organisms thanks to the appearance of specific cells, the Mesozoic witnessed the emergence of new species such as mammals, birds, dinosaurs of course, and angiosperms. The latter are plants that can form flowers and fruits. This phenomenon has an enormous impact on the terrestrial ecosystem. Divided into 3 periods, the Triassic, the Jurassic, and the Cretaceous, the Mesozoic began on a single continent, Pangaea. Then as the periods progressed, lands were to break up, fall apart, drift apart and create the geographical world we know today. In the Triassic period, all the continents were united in a single land called Pangaea. But little by little, 2 groups separated to give birth to Laurasia and Gondwana. The climate becomes more changeable. There are tropical areas, others more temperate and dry, and arid areas. There seems to be also more marked summers and winters. The fauna and flora have adapted to these new conditions. At the base of the food chain we find sponges, polyps, crinoids. Insects will also become more and more abundant, especially in the Jurassic. These animals allow others to survive, especially fish. We are here during the first phase of the Mesozoic. On the geological timescale, the Triassic is between minus 252 and minus 201 million years ago. The average temperature is 18 degrees Celsius or 64 degrees Fahrenheit, but it can vary depending on the region. Some are desert, others are affected by the monsoon. The icy areas are very sparsely populated. The temperate areas are already more livable. But it is especially in the tropical zones that life is the most effervescent in the ocean. The atmosphere consists of 18% oxygen, but contains very little CO2, only 0.25%. The climate was warmer. During the entire Mesozoic, the Earth did not experience glaciation. The ocean tries to reconstitute the reefs, the first underwater habitat for a large part of aquatic species. Tetracorallian corals have been largely wiped out. Little by little, hexacoralliar corals are taking their place. Here you can see calcareous algae supporting the corals in the hard work of building a reef. Soon life will be able to flourish again. In the Triassic, species that had tried to develop in the Permian finally managed to make a place for themselves in this world. Ammonites and sea urchins, for example, diversify and proliferate. Look, right there. You can see a Crioceratite's Emeraceae. It is part of the ammonites. It is called unrolled ammonite. You can probably understand why. Its shell rolls up on itself and forms an effective protection against certain predators. A little further on, another ammonite, Ceratites semiparatus, goes in search of food. The Mesozoic is often called the Age of Reptiles. In the Triassic period, reptiles will compete with vertebrates. On land as well as in the sea, they take over. This group of reptiles looks a bit like dolphins. They are ichthyosaurs. There is a Californosaurus, and a little further on, an Utahtsasaurus. These marine specimens were between 1 and 10 meters long, that is to say, between 3 and 30 feet long. They fed exclusively on fish. As you can see, these species were viviparous. This female is in the process of expelling her young. In the predator category, ichthyosaurs had to share space with Nothosaurus. This reptile is semi-aquatic. It is a Nothosaurus. It looks a bit like a lizard. Look closely at its legs. They are equipped with webbed toes. It can therefore easily swim, but also move on land. It has a long neck, a long snout, and very fine and pointed teeth. Its tail was used as a propeller to move in the water faster. Its favorite food is fish, but it sometimes feeds on other marine animals if it has nothing else to eat. Even if it is adapted to swimming, it lays its eggs on dry land. It is not fully adapted to aquatic life, although it does quite well in the water. It lives on the shore and spends part of the time out of the water when necessary. Here is Ceresiosaurus calgagni, which presents itself to us. In it, we don't see any toes anymore. They have been replaced by real fins. As you can see, his neck and his tail are very long. He is a very good swimmer, and he is also very fast in the water. This is a valuable asset for hunting. It lives in lagoons alongside the Nothosaurus, the Pachypleurosauride. It is one of the largest marine vertebrates of the Triassic. These small water lizards lived only in the Triassic. Here is a small Caecosaurus. This elongated animal could be up to 1 meter or 3 feet long. Its limbs are paddle-shaped. They allow him to move in the water with a disconcerting ease considering his size and weight. In the family of Pachypleurosaurs, we also find the Ankylosaurus and Dactylosaurus. They are the first of this family to have lived in Europe. The Sirpianosaurus lived in the same regions. We will now have to leave this small world to discover the Jurassic. The Jurassic follows directly after the Triassic. This period is very favorable to marine species. The transgression begins and invades a large part of the continents. You must first observe the flora in order to note and understand the changes that took place. Radiolarians, such as Ellipsocophus or Saturnalis, are unicellular planktonic animals a few hundred micrometers in diameter. They provide the silica necessary for the green algae that proliferate. Radiolaria would have appeared in part thanks to underwater volcanic eruptions. These small and complex organisms are as useful as they are beautiful. Look at this, Sagonacena stellata. When the soft parts die, this is what you can find as a structure under the sea. This is its skeleton. The star formation is magnificent. These small, radiolar organisms abounded in the Jurassic. The most likely reason for this abundance would be the upwelling of deep cold water. Rich in nutrients, they bring back to the surface of the ocean many nutrients. Radiolaria are also symbiotic species. Algae, unicellular or dinoflagellate, live in harmony with these siliceous marine plantlets. In the middle of these algae lives a Hildoceras bifrons. This small predator catches its prey with its tentacles. For the moment, it does not seem to be hunting. He surely had dinner a short time ago. That leaves us all the leisure to observe it a little more closely. Its shell is in flattened spiral. You notice that it is very ribbed and all in relief. Inside there are chambers. These are filled with air and allow the buoyancy of our Hildoceras bifrons. This specimen is probably a female. The females are bigger than the males. They measure between 95 and 175 millimeters, while the males do not exceed 40 millimeters. Here is a Stenopterygius. It is part of the ichthyosaur family that we have already met. Its appearance and behavior are very similar to those of dolphins. It swims most of its time in deep water. It hunts and feeds on fish, but also on cephalopods, mollusks equipped with tentacles. The specific cells have largely developed and refined since the Cambrian. Our Stenopterygius has a skin composed of two distinct layers, the epidermis and the dermis. It also has a layer of fat that allows it to preserve the internal temperature of its body. But let's not linger too long. We have an appointment with a Plesiosaurus, and he doesn't like to wait. Here is Elasmosaurus platyurus. He is a member of the Plesiosaur family, the long-necked marine reptiles. This one is 7 meters or 22 feet long, but it can easily reach 15 meters or 50 feet as an adult. Inside its neck are more than 32 cervical vertebrae. One would think that their barrel-shaped body, long neck and small legs would not help them much in the ocean. But despite appearances, this sea monster is quite agile and very powerful. First of all, its legs are also fins. These allow him to swim a bit like turtles. It explores the oceans and does not limit itself to a given territory. It is lively and has a very powerful jaw. It quickly became a feared predator in the 4 corners of the globe. Not far from there, another member of the Plesiosaur family prowls around. It is a Morternaria simorensis. It has not adopted the same diet as the other members of its family. As you can see, its jaw and teeth are totally different from Elasmosaurus platyurus. It has long, thin, and mostly outward-facing teeth. After several years of study and research on the skeleton of one of them, we now know that this particular specimen of plesiosaurs feeds in the manner of baleen whales by filtration. When it opens its mouth, it captures a large quantity of water containing krill, tiny shrimps, small fish or small shells. It rejects the water through its teeth and retains its breakfast. For the small anecdote, the plesiosaurs would perhaps not be all extinct. The Scottish legend of Loch Ness affirms that one of them, named Nessie, would still live there. The microscopic algae that serve as the building blocks of the marine food chain are growing at a staggering rate. You can't see them with the naked eye, but this water is teeming with Coccolipherida. This is a single-celled green algae surrounded by a carapace of calcareous test formed by discs. These algae constituted the main part of the phytoplankton in the Cretaceous period and were the basis of marine ecosystems. They benefit the large groups of invertebrates still present in the Cretaceous. Mollusks such as ammonites or rudists, sponges, echinoderms such as holothurians, crinoids or sponges, and cnidarians, jellyfish, corals, multiply and diversify. More numerous, they allow other animals, especially vertebrates such as fish, sharks, and marine reptiles to survive, multiply, and develop in turn. At the top of the food chain are the reptiles. The ichthyosaurs decline to the benefit of the plesiosaurs and mosasaurs. The Hydrotherasaurus you see fishing in the middle of this school of fish is a plesiosaur. It is 13 meters or 40 feet tall. Its head is only 33 centimeters or 12 inches long, but its neck has no less than 60 vertebrae. It uses its limbs as paddles. It can move vertically, horizontally, and even turn thanks to its legs' fin. It just needs to accelerate its pace to propel itself on a prey and capture it. This animal is very impressive. Look at the way it moves. But let's go back to the surface a little. See that reptile? It's a Mosasaurus. He's got his eye on that pteranodon. The bird is busy watching a school of fish and doesn't see that it's at the mercy of the reptile. He catches it in a fraction of a second. This mastodon is a Tylosaurus, Mosasaurus. It is close to the varan and the snake. With him, everything seems to be disproportionate. It has a morphology adapted to predation. Even its tail is incredibly muscular. It is equipped with 2 pairs of fins, and they are very efficient. He is an outstanding swimmer. Skilled, fast, and powerful. Another particularity of the Tylosaurus is that its head is long, as well as its body. As you can see, its snout is marked. It must be said that these mosasaurs are known for their ferocity. They could attack other predators or fight with their own fellow creatures. The fights were terrible. They fed on fish, but also on seabirds, sea turtles, and even plesiosaurs. We will leave the Cretaceous with this god of the seas. Our journey through time and the ocean ends here. At the end of the Cretaceous, the Earth is hit by a giant meteorite, which, by darkening the atmosphere, causes the collapse of the primary production of the oceans. The different animals of the food chain are starving. The famine kills. Ammonites, rudists, non-avian dinosaurs, and many others are wiped out from the biosphere. Nothing will ever be the same again. But all this, you will have perhaps the chance to discover it in another journey.